recording here. So section 4.1 deals with vector spaces and subspaces. And in our last class on Tuesday, we introduced section 4.1 and looked at a few examples. We looked at the axioms for a vector space. And now we also looked at a subspace. A subspace is a subset of a vector space. It could be the actual vector space itself, because a set is a subset of itself, technically. And subspaces, there are three axioms that have to be satisfied, three conditions. And if you look in your ebook, on page 195, they talk about those three conditions. And we're going to reiterate those three conditions in this example. So let me give you a moment to copy this down. Christina, you're seeing the page okay? Okay. So, okay, Westina. Okay. And of course, this is being recorded. All right. So, in this problem, we're going to let V1 and V2 be in a vector space V. And you notice this is very sort of general. We're not saying the vector space is like R2 or R3 or R4 or, the polynomial space. We're just saying it's a vector space. But what we're going to do is we're going to define this space H to be the span of the two vectors, V1 and V2. What we want to do is we want to show that H is a subspace of V. Show that this space H is a subset of V. Okay, so like an example, just kind of a little example of a subspace, just so, if you had, like, say you had the span of vector 1, 0, 0. Okay, 1, 0, 0. And 0, 1, 0. Okay, let's say that, let's call this space W. So this is a separate thing that I'm doing here. It's not like, well, when we talk about like a subspace, okay, I find it helpful, and I think you will too, to think of an example of a subspace, a concrete example. So what I've done here is I've written W equals the span of the vectors 1, 0, 0 and 0, 1, 0. We know those as vectors E1, and I'm trying to write very neatly here so that it's legible. It's not like a typed document, but it's legible. Okay, so where do those vectors E1 and E2 live? Do they live in R2 space, R3 space, R4 space? Where do they live? W is not, I just call this space W instead of H. I'm just calling this space here, this is a space, and it's a subset of R3. Okay, if you take the span, a span is all linear combinations of 1, 0, 0 vector and 0, 1, 0 vector. That's going to be a subspace of R3. Now for R3, for all of R3, what extra vector would we need to have in our span? What extra vector would we need? If we wanted to generate the R3 space, in other words, that's right, Matthew, that's right, Solomon. We would need 0, 0, 1 to be added in our span so that the span then of E1, E2, and E3, that would be equal to R3 because the span of E1, E2, and E3 is all linear combinations of IJK, or some of you, or E1, E2, E3. And any vector in that span would, I mean, any vector in R3 can be written as the span of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. But in this example, I'm defining my space W as my big space W here as the span of 1, 0, 0 and 0, 1, 0. And that's going to be a subspace of R3. This is a subspace, right? We know subspace or subset. I mean, it's actually a subspace, but it is a subset of R3. Now, what's it look like? What's that space look like, this subspace W? What's it look like? In R3, I mean, if we had to geometrically describe this space W, this subspace, what's it look like? That's right. That's right, Mikhail and Solomon. It's a plane. It's a plane in R3. Okay, and the plane contains what axes? What axes are contained in the plane? You got the x1 axis, x2 axis, all right, so xy axis or x1, x2 axis. So this space W contains the x1, x2 axis. So the reason I'm just mentioning this is because when you hear subspace, I mean, how many of you find it helpful to have a little example in your mind when you hear the term subspace? I mean, this example is okay, so that's what I'm looking for. Thank you, Binyam, Christy, Sega. That's an example of a subspace. And there are a lot of examples, but this is one that I always like to use. Well, so here what we're doing is we're defining the space H to be the span of two vectors. Okay, and we want to show that H is a subspace of the vector space V. So let's go ahead and show that. Are there any questions so far? All right. All right. Okay. So we need to show that H satisfies the three properties of a subspace. There are three properties that we need to establish. Okay. So the first property is the zero vector. The zero vector, is it in this space H? The space H we've defined as the span of two vectors. Would the zero vector fall in that space? The answer is yes, because the zero vector can be written as this is a zero here. It can be written as 0 times v1 plus 0 times v2. But I could write the vector 0 as 0 times v1 plus 0 times v2. We can do that. And the 0 times v1 plus 0 times v2 is in our space H, because H is the span of two vectors. And the span is any linear combination of the two vectors. Well, 0 times v1 plus 0 times v2, that's a linear combination of v1 and v2. So therefore, the zero vector is in our space H. So far, so good. So far, so good. Okay. All right. Are there any questions so far? Okay, well, the next thing we need to ask then is this space H closed under vector addition? That's the second condition that we need for a subspace, is that the space is closed under vector addition. Okay, so we need to try to prove that it is. So what do? We're going to pick two vectors in our space H. Of course, any vector in space H would be a linear combination of v1 and v2, because any vector in space H is in the span of v1 and v2. So what we'll do is we'll define a vector u to be c1 v1 plus c2 v2. No. So Matthew, the w that I had on the previous page has nothing to do with this w. That was just space w. This is vector w. So this w here, it's a good question. This w here in part B has nothing to do with that little example that I did. The only reason I did that little example was so that you could have an idea in your mind of an example of a subspace, and I called that space W. But now that's like in the past, and now there's no space W. There's only space H. And okay, and so I'm defining. Good question. I'm defining two vectors, vector u and vector w. Both are in the span of v1 and v2, clearly, because both vectors are linear combinations of v1 and v2. So, okay, what do you think I'm going to do with these vectors u u, and w. What do I want to do with those vectors? If I'm going to show that our space is closed under vector addition. Yeah, that's right. Sega, Solomon, Divhar, and Binyam, I want to add them up. Okay, let me add them. So u plus w would be c1v1 plus c2v2 plus d times v1 plus d times v2. Now what we can do is we can rewrite this summation. We can put the c1, we can just reorder the sum and write it as so u plus w is c1v1 plus d1v1 plus c2v2 plus d2v2. Okay, but then notice I can write this sum this way. I can write u plus w to be equal to c1 plus d1, that's scalar, times v1, plus c2, sorry, u plus w would be equal to the scalar c1 plus d1 times v1, plus the scalar c2 plus d2 times v2. Well, so is u plus w in the span of v1 and v2? That's right. So therefore, u plus w is in H. And so this space H is closed under vector addition. It is closed. Any two vectors in the space, you add them, you're going to get a vector back in the space. It's closed under vector addition. That is correct, Matthew. U plus W is a linear combination of V1 and V2. That's absolutely right. Absolutely. Please let me know if you have any questions. If U plus W was not a linear combination, Matthew's wondering what would it look like if U plus W was not a linear combination. Well, maybe if there were like plus, I got to be careful here what I write because I'm not actually. I never thought about it. I've never thought about it, but you know, it'll be kind of obvious when you do the homework. As Binyam's saying, it'll be kind of obvious. All right, let's move on here. Are there any questions? We're in section 4.1. Okay, there's a third condition now that we need to check. Third condition is H, is my space H closed under multiplication by scalars? Okay, is H closed under multiplication by scalars? This is the third condition for a subspace. Okay, well, what we're going to do is I'm going to let my vector U be equal to B1, V1 plus B2 times V2. So, you know, that vector U is in my space H. It's in the span of V1 and V2. I'm going to take that vector U and multiply it by a constant. Okay. What do you think I should do with this constant here? What's the natural thing to do with a constant? I'm drawing a distribute. Good, yeah. Yep, that's right. And so I will distribute that constant, and look what I get. The vector C times U equals C times B1, that scalar, times V1, plus C times B2, that scalar, times V2. In other words, the vector Cu is equal to C1B1 times V1 plus C2B2 times V2. And CB1 and CB2 are scalars. So does the vector Cu, is it in my space H? Is it in the span of V1 and V2? It is. So therefore, Cu is in space H, and space H is closed under multiplication by scalars. And you've satisfied the three conditions for H to be a subspace. Okay, and in general, I have it show nicely here. In general, the span of any number of vectors is going to be a subspace. So we proved it for the span of two vectors. We proved this result. But if we had the span of three vectors, we could prove that. We would just do the same steps that we use to show that the span of two vectors is a subspace. We can do the same. We could do the same. Use the same approach to show that the span of three vectors is a subspace, or the span of four vectors is a subspace. It would be the same approach. So basically, and I think you can intuitively see that. It wouldn't, like for instance, it wouldn't be too hard to show that the span of three vectors is a subspace, right? Using this approach. So the span of any two vectors or more is a subspace. The span of one vector is a subspace. If you had the span of V1, that's a subspace. So the span of any number of vectors is going to be a subspace. And it'll be a subspace, hold on here, one moment. This is actually theorem 1. Theorem 1 in the book, it'll be a subspace of some vector space V. I'll add those words, of some vector space V. Okay. Is the zero vector also a subspace? Man, that's a good question, Binyam. I never even thought about that. Let's see. I never thought about it because it's not too interesting to me, but the zero vector is a subspace of V. It is. Well, we're talking zero vector, just a vector. And you can prove it to yourself. You know, if you add 0 to 0, you get 0. If you multiply a constant by the zero vector, you get 0. And 0 is equal to 0. So yeah, I mean, what I mean is if you multiply a constant by the zero vector, you get the zero vector. So what's being asked is the zero vector a subspace? Well, if the space that consists of the zero vector includes the zero vector, so the first condition is satisfied. Second condition, if you, let's see here, that it's closed under vector addition. I want to be a little careful. I'm sorry, I want to be just a little bit careful before I mean, my thinking is yes, but I just want to be a little bit careful because sometimes when I answer too quickly, you know, I don't get the right answer. But I think it has to be, as Binyam said. All right, are there any questions on this problem? All right, well, let's go ahead and you're welcome, Binyam. You're welcome. Let's go ahead and move to an example here. Okay, take a moment and copy this example down. Okay, so the span of zero vectors is subspace. I don't. Oh, yeah, I don't think we have to have one vector, Matthew. You have to have one vector, because if you have no vectors, you know, you don't have anything. You know, you don't have a span of anything. So you have to have one vector. All right. So, wow, this is an interesting space here. This is my space W. Okay, so I'm not calling it space H. I'm calling it W. But I could have called it space H. And W is the set of vectors that all the vectors have to be of that form. Have to be of that form. S and T are real. They're real numbers. S, comma T, real. That means they're real numbers. So let me ask you this. S and T are real. So let me just write something here. Hold on. Let me just write something. One moment. One moment. I'm writing a vector here. One moment. Okay. Is this vector 0, 11, 5, and 4, is that vector in W. Well, you shouldn't need to do that much, Binyam. I hear what you're saying, but Solomon thinks yes. Solomon thinks yes. I'm not saying it's yes. I just, well, you know, I just came up with this vector. So this is now, what I'm doing here is not formally part of this determining if that space W is a subspace, but clearly the space W, there are conditions on the coordinates. And so what I did was I'm just asking, hey, here's a vector. Here's a 4x1 vector. Would that be in space W? So look at the first two entries here. Look at the s minus 2t and the 3s plus 5t. If it's going to match the 0 and the 11, what would s have to be? Okay. So all right, t is 1 and s is, so let's see, Binyam and Solomon are, so Binyam, you were right. Now Solomon agrees. So s equals t, s equals 2 and t equals 1. If s equals 2 and t equals 1, I get the first two entries. So I guess I'm good then, right? What about the third entry? Does that work? Yeah. 2 times 2 plus 1 is 5. But the fourth entry, that doesn't work. The fourth entry, right? Because 4 times s is equal to 2. 4 times 2 is 8. So if this 4, if I change this 4 to an 8, then this vector would be in W, right? So this is a very, you know, well, that's okay, Binyam. I welcome all input. I welcome, and sometimes it's natural to just think about doing an augmented matrix, but you know, sometimes you don't need to. And in this case, so what I'm trying to demonstrate to you is that this space W is a subset of what? It's a subset of R, what? R4. But is it equal to R4? Is it equal to R4? No, because we just found a vector, you know, here it is. We just found a vector that is not in space W. That vector, this vector here is in R4, but it's not in this space W. All right. So we want to see if the given set, no, well, we haven't proven that, we haven't proven yet if this space is a subspace or not of R4. We haven't proven that yet, but I'm just trying to help give you an intuitive feel for section 4.1. And I find examples are very helpful. If yeah, so okay, well, all we know right now, we know the three conditions that we can use to prove that if a space is a subspace or not. We know the three conditions, and we also have a result that if I can write the space, if the space is a span of any set of vectors, then that space is a subspace. Could I write space W here as a span of some vectors? That, yeah, Binyam, R4 is only wide enough to equal itself. Right? R4 is but space W, as you know, is not. It's a subset of R4. It's a subset. That this is what this means, right? This symbol means subset, but we're not saying it's a subspace. Well, I'll tell you what we'll do. See, what I want to do, rather than use the three conditions to prove that space W is a subspace of R4, rather than like use the three conditions and do a formally prove it, show that, you know, space W is closed under vector addition and multiplication by a scalar, and that the zero vector is in space W. I'm just gonna do this. I'm gonna let you be. I mean, we could prove it. We could prove it like we can show that the three conditions for a subspace hold for space W. But also what I could do is I can say, let U be in space W. If a vector used in space W, then for some real values S and T, U would be able to be written as this 4x1 vector. But notice this 4x1 vector here, I can write it as S times 1, 2, 3, 4. I can write that vector as S times the vector 1, 3, 2, 4, plus T times the vector -2, 5, 1, 0. But what is that? What am I showing that the vector U that's in space W can be written as a what? It can be written as a linear combination of vectors V1 and V2. Right? Very good, Binyam. Very good, Matthew. And so W is equivalent to the span of those vectors V1 and V2. And that shows that W is a subspace of R4. That shows that W is a subspace of R4. Yes, it's a very neat connection. I agree, Binyam. So how many kind of like doing this approach to show that a space is a subspace? Yeah, Robin likes it, Christy likes it. Sure. Absolutely. Okay. All right, let's see if there are any other questions here. I mean, this is some of the most beautiful stuff, beautiful math you're going to see, in my view. I mean, of course, all math's beautiful, but, you know, we're not restricted to three-dimensional space like in Calculus 3. I mean, I love Calculus 3, but in linear algebra, we can have four-dimensional space, five-dimensional space. No. Now let's see. Matthew says, when would we ever have a case? Okay, I'll show you a case of that. Matthew wants to see a case where that would where you wouldn't have a subspace. So for that, I'm going to go to the whiteboard. But are we okay? May I move forward here? All right. So let me go to the whiteboard. And let me write down a space W that equals this. S 4 and T. Okay, this is coordinates S, T, and 4, where S, and I guess I'll use colon here. Okay, where S and T are real. Is this a subspace? We know it. We know it's a subset of what? It's a subset of R3. Good. It's a subset of R3. But is it a subspace? This is a colon here. Is that a subspace? Solomon thinks not. Noah thinks not. Why not? Why not? What does a subspace need to? Okay, the 4 is a problem. So what is? Okay, the 4 is a problem. Well, I'm not worried even about a linear combination. The thing is, you see, you got to be a little careful because a linear combination of vectors is a span of vectors, and that's going to be a subspace. But you can have subspaces that aren't linear combinations of vectors. You can have, weird different kinds of subspaces. So we have to, well, I got to be a little bit careful. At least, put it this way, at least it's possible. Okay. The span of a set of vectors it's classified as a subspace, but that doesn't mean there are not other different kinds of subspaces. But there's one thing that's not in W. There's a very important vector that is not in space W. Zero vector. That's right, Noah. Very good. So since the zero vector is not in W, W is not, it's not a subspace. It's not a subspace. Getting better with this mouse. Just going a little more slowly. Okay, so there's an example of a space that's not a subspace. Okay, and they're all for me. I don't, I mean, this is this is good enough. Again, the fact that we have to be a little careful. We can't say necessarily that if a space isn't a span of vectors, it's not a subspace. I want to be a little bit careful about that, because there are like let me see here. I'm just looking. I want to be a little bit careful here. In the book, for instance, they talk, like in exercise 21, they talk about a set of matrices, 2 by 2 matrices. Okay, they talk about a set of these special 2 by 2 matrices where you have A, B along the first row and 0 and D along the second row. They're saying the space of those matrices is a subspace of the set of 2 by 2 matrices. So I don't believe a span would be involved in that. So we have to just be a little bit careful about generalizing. But okay, are there any questions before we move on? All right, let me show you here. One moment. Okay, hold on here. So Matthew's wondering about the zero vector, the fact that it's not in the space. How does that show that we don't have a subspace? All right, bringing up the definition of subspace from chapter 4, from section 4.1. Okay, hang on. One moment here. Okay, so this is why. This is the conditions for a subspace that are necessary. And I always mess this up. Hang on here. There. So the fact is, I mean, these are the general conditions. The zero vector, that A condition for subspace, the subspace H has to satisfy those 3 properties, and we talked about those properties in the last example we did, and we proved that a span of vectors is a subspace. The zero vector is, if the zero vector is not in the space, you don't have a subspace. And that's, so Matthew, you're a little more comfortable now with that? Seeing these conditions in, all right, excellent, excellent. Okay, well, then if there are no more questions, let's go ahead and talk a little bit about section 4.2. Hold on, wait. One moment here. You mean the last example or the example before that? Oh, you mean W? Well, W could be written as a span of vectors. That space W was able to be written as a span of vectors in the last example we did. And we proved in the example before that, we proved that a span of 2 vectors was a subspace. And in general, a span of any number of vectors is a subspace. Well, you have to have 1 vector in there, right? At least 1. But all right, so and naturally the how many of you are going to maybe go back and listen to this recording again? Hopefully you're a little bit at least reasonably comfortable, but how many might go back and look at the recording again? Okay, so Sega, Christy, yes, absolutely, and Ryan. I mean, I kind of look at this. There was a movie I watched a few weeks ago, and the first time through, there was a lot I didn't. Well, I don't want to say there was some that I didn't understand, but when I watched the movie the second time, oh, there were things I picked up. How many maybe have noticed that about movies? Um, sure, sure. So it's maybe a good analogy. Let me stop the recording here.